Another property that we are going to talk about now, other than the atomic size, is the ionization energy. The ionization energy is the energy that it takes for an atom to let go one electron so that you have a cation left. The energy involved for this process, for going from a neutral atom to an ion so that you remove the outermost electron, that energy is called the ionization energy. And usually we will label IE1 referring to that's the first electron that we removed. You could remove more electrons like IE2, that would be the energy required to remove the second electron. So let's see how the ionization energy changes in the periodic table. And here you can see that going from left to right in the periodic table, lithium, beryllium, boron, carbon, nitrogen, oxygen, when going from left to right, it mostly increases. And I say mostly because there are two exceptions, from beryllium to boron and from nitrogen to oxygen. Then as we go, and we can put more rows if you will, as you go from higher to lower, this may be a little bit confusing, so let's just choose one column. And here, how does it change? It looks like we said that it increases when going from left to right, it decreases when going from up to down. Okay, so this is the general trend, and as we said, with some exceptions. The exceptions, if you remember, so beryllium, boron, why is it that this is not increasing? Why is it that nitrogen and oxygen does not increase? So the general trend is, we can just write it here, if this is the periodic table, when going from left to right, the ionization energy will increase. It means it takes more energy to remove the electron. And from going from lower rows to higher lows, higher number of rows, the ionization energy will decrease. It means it takes less energy to remove the electron. And there was that exception. Why is it that, I remind you, why is it that the nitrogen and oxygen, or beryllium and boron, do not follow that trend? It's because of the stability of half full or completely full shells. Notice that nitrogen, being a 2s2 2p3, has a half full shell. Oxygen is a 2s2 2p4. It is not a half full shell. So this is fairly stable, therefore it takes more energy to remove this electron. Now let's see, why is it that the general trend is the one we just said, that as you go down, why is it that the ionization energy decreases? Well, think about how in the nucleus, the farther away you put your electron, the less attracted your electron will be. So why is it, as you go down from the periodic table, why is it that the ionization energy decreases? It's because, so hydrogen, lithium, sodium, potassium, the electron here is in the 2s, the electron in sodium is in the 3s. This one is farther away, therefore less attracted by the nucleus, therefore it'll take less energy to be removed. Conversely, why is it that as you go from left to right, the ionization energy increases? Well, think about that as you have one nucleus, and let's say from lithium to beryllium, notice that the electrons, say that this is the 2s, for beryllium is 2s1, sorry, for lithium 2s1, 2s2 for beryllium. The 2s, if you go to beryllium, you're adding another charge, and the electron is still there. So since you're adding another charge, notice that the same factor that made the atom smaller, right? Remember that when going from left to right, the size decreases. The same factor that makes that atom smaller makes the electrons more attracted, therefore it'll take more energy to be removed. The moment they are smaller, they're closer to the nucleus, they are more attracted to the nucleus. So let's just solve some of these questions. In this case, it's asking to rank the following elements in terms of decreasing ionization energy of the first electron. So let's take this one first. So krypton is here, helium is here, and argon is here. The general trend is if you go down the periodic table, the ionization energy decreases. It's easier to remove the electron. This means that the hardest will be the ionization energy of helium will be higher than the ionization energy of argon, and this one will be higher than the ionization energy of krypton. Okay. Now let's take another one that may be a little bit more intricate, like iodine. Iodine is here, and then xenon, and then cesium down here. Well, we know that as if we go to the right, it'll take more energy, so we know that the ionization energy of xenon should be larger than the ionization energy of iodine. And because so iodine and xenon are in a separate row, it'll take less energy for cesium, so the ionization energy of cesium is lower. Sometimes there are some exceptions. This is why, again, what's important here is not to know the general trend, is to understand why there are some exceptions. Okay, and we will have to think about how electrons and nuclei attract each other and how far they are so that we can explain the exceptions.